power analysis. And we're, it's a departure. I mean, it's very related to what we've been talking about, but it's approaching what we've been talking about in a very different way. So it's really something that you need to think about right up front before you even start an analysis. And one way of thinking about the question is, how big a sample do I need to detect a noteworthy effect of X on Y? Right? It's an incredibly important question. If you, let's say you have a great idea for some sort of classroom intervention, and you run the intervention, you do random assignment, it's just, it's perfect. It really ran well. And let's say that you run the regression of the outcome that you're most interested in affecting as a function of being randomly assigned to the treatment or control group. Let's suppose in standardized units that B1 is 0.25 standard deviations. That in education research is a noteworthy effect, believe it or not. We'll talk a little bit more about that in a second. But suppose you've generated a quarter of a standard deviation effect and your standard error is 0.20, right? If you've got a fairly small sample, you could easily have a standard error that's that large. And now you're stuck, right? You can't be confident that you've actually generated a noteworthy effect, because with this standard error, you can't reject the hypothesis, the null hypothesis, that there's no effect, right? Your best estimate of what the effect is a quarter of a standard deviation, but you can't be very confident at all because a 95% confidence interval includes 0, right? So no one's going to be impressed by 0.25 if the standard error is 0.20. Standard error is a function of sample size. The larger the sample size, the smaller the standard error. And so, you really want, in this case, a sample that's big enough to detect a 0.25 standard deviation impact, right? And that's what power analysis is all about. All right, so let me talk more broadly about what a noteworthy effect is. In psychology, there are what are often termed Cohen's rules for effect sizes. And these can be intervention effect sizes. They can be standardized regression coefficients. And his rules are 0.80 is large, 0.50, this is standard deviations is medium, and 0.20 is small. So what do I think of Cohen's rules? Well, that's what I think of Cohen's rules. It doesn't make any sense. It comes from psychological research where, partly where, if you run these little experiments and look 10 seconds after the experiment's done, you can get these much bigger impacts. Or if you're dealing with cross-section data, you can get these pretty large standardized regression coefficients. The economist in me, in thinking about what is a noteworthy effect, doesn't want to know just what the impact is, but I want to know what the impact is relative to the cost. right? So, there are incredibly expensive interventions and there are incredibly inexpensive interventions. So people have been doing a lot in the post-secondary world of these various psychological interventions of trying to, for example, promote sense of belonging among first-year students. It's a big problem. People come into, often first-generation students, they come into college and really wonder, do I belong here? And these kind of interventions are a way of instilling a sense of belonging. Mindset is another example where there have been experiments where if you get students to come to believe that you're as smart as your effort has led you to be, where it's very much a function of effort and not just some people are born smart and some people aren't. There are various kinds of social psychological characteristics that are manipulable, right? And take sense of belonging. People here in the school did a sense of belonging intervention on first-year biology students at UCI. And it's maybe 50 cents per student to run this intervention. It's done. You get a 1 credit on your grade or 1 point on your grade to take it. People do the 30 minutes or whatever it takes. Under those circumstances where it's very inexpensive, if I generate an impact, let's say of 0.05 standard deviations or 0.10 standard deviations for such a cheap intervention, that's a big impact. On the other hand, if I'm doing some kind of psychological intervention that requires cognitive behavioral therapy, hours and hours of kind of one-on-one interactions with a professional, you can easily have a $10,000 per child or per youth intervention. And for that, if it costs so much, you should be demanding a much bigger bang for your buck, as it were, a much bigger standardized impact. So having these straight up rules independent of context don't make sense to me. But you'll run up against them. People will do some kind of analysis, standardized coefficient, and it'll be 0.35. Well, it's in between small and medium, they'll say, and they'll cite Cohen, Cohen 1988. So anyway, you'll run up against that, but regard them with skepticism, because it's really hard to make context-free generalizations about effect sizes. So for the particular question that you're asking, you really do need to first, before you even think about designing an experiment, or think about getting using a data set that you might know about. Is this come upon some data set? Is this data set is it big enough to tell me what I need to know? And what I need to know is whether a particular relationship is a noteworthy relationship. And that comes from looking at the literature. It comes from other kinds of considerations that will tell you what kind of effect you should be trying to target with the analysis that you have. Target in the sense that you've got a big enough sample so that if that's the effect, you'll be able to detect it. That's what a power analysis is all about. And a more intuitive way of asking the power analysis question is talking about this noteworthy effect as a minimum detectable effect size. This is all the Bloom article for this week. So a minimum detectable effect size is the smallest true impact that your regression or experiment has a good chance of detecting. Okay, so if you, after reading the literature, consider 0.25 standard deviations to be a worthy impact to aspire to attaining, 0.25 standard deviations. You want to know if that indeed is true, that if your experiment generates exactly a 0.25 standard deviation impact, or if your standardized coefficient is exactly 0.25 standard deviations. If that's true out in the world, is your regression analysis of data going to be able to detect an effect that large or small, 0.25 standard deviations? And it's in terms of having a good chance, and what's usually considered to be kind of the standard, what's a good chance? It's an 80% chance. All right, so when we talk about significance of coefficients, we usually are talking about 90%, 95%. But in the minimum detectable effect size literature, the standard is usually 80%. So you want to have a sample that's large enough to have an 80% chance of detecting this target effect size, 0.25, if that target effect size is real out there in the world. All right. And even if every time someone ran an experiment of the kind you want to run, or a standardized regression coefficient, even if out in the population, 0.25 is exactly what that experiment gives you, or that standardized coefficient gives you, just the fact that you're going out and not taking a population of the whole world and running this experiment, you've got a sample from it, right? And there's sampling error. So even if 20.25 is really the case, there's not a 100% chance that it's going to show up in your statistical analysis every time. There's always some chance that you, through bad luck, have drawn a sample that gives you something that's less than 0.25, right? So you want not 100% certainty, but you want a good chance of being able to detect this 0.25 impact. And as I say, good is typically taken to be 80%. You can make it 70% and 90%. It's a parameter that you can vary when you do your power analysis.
Yes.
Please.
Okay. So practically, when you're kind of finding how big of a sample you need to detect a noteworthy effect, how do programs like the ones on the problem set actually do that? How do those work?
That is the next thing we're going to turn to. So you'll see them work, but it's really, as the Bloom article kind of describes, it's just a straight up application of statistics. It's a very kind of straightforward set of calculations. So these programs just all use the same kind of basic statistics to generate what the minimum, well, for a given minimum detectable effect size, what the sample size is going to be. So hang on and we'll see exactly how it works. Any other questions?
I have a question. I'm not sure about my question though, so I'll just ask it. So if we're looking for a minimum detectable effect size and we find an impact smaller than the minimum detectable effect size, then does that mean we don't know if it's true or not?
Well, this is all in the design part of your research, right? It's, should I even think of using this new data set that I found? that seems perfect. It's got everything that I want in terms of variables, but it only has 150 observations, right? Should I even think of touching those data, given the effect that I'd like to be able to detect, right? So once you've got the data and start doing your analyses, then you're getting regression coefficients, you're getting standard errors, right? And they will tell you, well, the coefficient estimate's going to give you your best guess at what the effect is, and then the standard error is going to give you a confidence interval that will tell you how confident you can be that it is indeed that number or around that number. So this is all about planning to do an analysis, designing your experiment, choosing to use a data set or not. And then once you make that decision and then do the analysis, then all the other things that we've talked about this quarter apply. Okay, so how do we go about doing this? Finding the sample size. One is we can use programs like GPower and Optimal Design. Those are the two that you'll be using this week for the problem set. They're both free, and the Optimal Design has a lot of features that handle clustering and other kinds of problems that often pop up in education research. Or pay attention to standard errors. Because there is an intimate connection between standard errors and power. And if you remember way back in maybe the second week, I had a little part of a lecture about standard errors, and I talked about how they can be a guide to multicollinearity. They certainly are a direct guide to how confident you can be that a particular parameter is real. But the last thing on the list was that standard errors are very useful for telling you something about power. So we're finally getting around to explaining why that's the case. But let's start out with these programs, the ones that you use for this week. So let me share my screen here. Okay, so I hope everyone increased the size of the screen a bit. I hope everyone, because this is what you get when you open up GPower. And there's all these options, but you want t-tests, and all the options are showing up here. You know, in all my years of using GPower, I've only used it to test differences between two independent means, two groups, right? So you have an experiment, you allocate people in treatment group and control group. Those are two independent means. Okay, type of power analysis a priori compute minimum sample size given significance level, power, and effect size. Okay, so let's start in on this. Typically, when people ask about minimum detectable effect sizes, and Bloom has an interesting discussion about this. You know, we're so used to two-tailed tests when we do confidence intervals. Bloom makes an argument that maybe we should, if we have an experiment where we have a directional hypothesis, maybe we should be using a one-tailed test. But for purposes of illustration, let's do a two-tailed test. So let's actually, let me provide a little bit of context here. Let's try to come up with a power analysis for an experiment that I've spent the last 6 years of my life working on. We needed to do a power analysis to get funding for it. It's called Baby's First Years. And it's an RCT evaluating the impact of $4,000 per year monthly, or well, they're paid monthly income supplements on children's cognitive functioning. So there are other outcomes we're looking at, but let's focus on children's cognitive functioning. And the idea was to recruit a certain number, and the number that should come out of our power analysis, certain number of women who low-income women, their incomes are below the poverty line in the calendar year preceding the births. We recruited them from birth hospitals. We gave them a screening interview to see if they were income eligible. And then we got consent if they were interested in participating in a lottery. And if they said, yes, I'm interested in doing that, then they were randomly assigned, it's an RCT, randomly assigned to $333 per month for 40 months, the first 40 months of their children's lives, or $20 per month for 40 months. All right, so everyone gets something. It's $800 in the case of mothers who are in the low cash group, we call them, but it's $333 a month, $4,000 a year, in other words, $333 a month for 40 months, 12,000 something dollars altogether. And the question is, does income supplementation in and of itself lead to changes in family functioning that in turn will benefit children's cognitive functioning? And our measurement of children's cognitive functioning was originally planned to be at 36 months. Turns out 36 months is starting this June, so we can't really be confident that we'll be able to bring kids into university labs that we've got set up to make these assessments. The assessments are kind of standard executive function tests, IQ tests, and things like that, plus EEG. That's a measure of the electrical activity of the brain. You put these little caps on kids and monitor their electrical activity for 5 minutes, and then you do an analysis to try to see how much activity there is in different portions of the kind of power spectrum that you can measure with these EEG caps. So it's different kinds of measures of cognitive functioning. And we want to know whether we want to power to detect a 0.20 standard deviation difference. Between children in the low and high cash groups. We say 0.20 because if you look at the literature, none of which really focuses on infants, but if you look at the literature on young kids, and it's mostly quasi-experimental literature, so when the earned income tax credit became more generous in the 1990s, how much, and it turns out to be an achievement difference for young kids between kids who were in families that received relatively higher payments versus relatively lower payments from the earned income tax credit. And the difference was about 0.06 standard deviations per $1,000 of additional income. So with a $4,000 per year supplement, that translates into about a 0.20 standard deviation effect size. So we wanted to be able to detect a 0.20 standard deviation effect size if it was truly out there. And we want to use the usual rules about 80% chance of being able to detect that. So we have 4 sites, New Orleans, Omaha, Twin Cities, and New York City. In each of the sites, we tried to recruit 250 mothers and newborns. It varied a bit from site to site, but altogether there were exactly 1,000 moms recruited over the course of 12 months. So that we had this 12-month recruitment cycle, so that as soon as we were done recruiting the very last infant and mother, the first kids and moms who were recruited, the kids would be turning 1. And we've got an age 1 assessment, we got age 2 assessment, age 3 assessment. So let's just concentrate on the age 3 assessment. It looks like because of COVID, this will have to be 48 months rather than 36 months. But that is a not important detail for the power analysis. The power analysis says how many cases do we need to have an 80% chance of detecting a 0.20 standard deviation difference between families that were assigned to the high cash group and the low cash group. Questions about the study?
Greg,
Yeah.
I have a quick question about, so like in this, like if you wanted to measure like almost even intent to treat in this example, I don't know if that would be something you wanted to measure, but because there was like a volunteer, like there was multiple measures for them getting in, and everybody is receiving something. I guess my question, like if you wanted to measure intent to treat, what would that look like in this study?
Good question. So, the intent to treat is all about offering people these two alternatives, right? And it turns out we were able to arrange with a debit card company so that we could hand the mother, when she's in the hospital, this is like the day after giving birth, handing mother the debit card that either has a $333 or $20 initial deposit. And then we tell the mother every single month from now on out for 40 months on your child's birth date, there's going to be a $333 or $20 a month loaded up. So the difference isn't between $333 and nothing, right? It's between $333 and $20. In other words, the treatment difference is $313 per month. But in terms of intent to treat, the intent to treat question, if you think about if you offer Head Start slots and only some parents take up the offer, we're offering this debit card that gets filled up with either $333 or $20. And only if substantial numbers of mothers after being given the debit card didn't use the debit card would there be a difference between intent to treat and treatment on the treated, right? In fact, almost everyone, all but 5 or 6 of the moms have used the debit card. We've got a little operation set up so that if moms have problems with the card, if they lose their password or anything, they just call up and we kind of troubleshoot. So almost everyone is using the card. The few people who aren't, there are more of the $20 rather than $33. And there's some indication that $20 moms use the card to kind of save up across a number of months and then spend it. So we don't really know. It looks like there's virtually universal take up. So it is an intent to treat analysis. And the people who were treated are almost completely congruent with the people who were offered a chance to participate. So it's one of those rare cases where you don't have compliance problems. Everyone complies with the experiment in the sense that they take their debit card and they're using it. Is that clear?
Yeah, that makes complete sense. Thank you.
Okay. Other questions?
I have a question. I'm curious to know if you looked at what they spent the money on.
Yes, we're curious. There's all sorts of consents that the mothers are given the option of consenting to or not. One of them was, do you consent to allowing us to use information about how you spent the money on the card? And about 80 some percent of the moms said, yes, that's fine. So we've got all the expenditure records for almost all the moms. And we don't know what they bought, but we know where they made the purchases, right? So you can classify, is it a big box store? Is it a drugstore? It turns out, especially for the high cash gift group, a third of the money is taken out at ATM machines, which is fine. But you don't know how that money's spent, right? So our hopes of being able to track expenditures using this debit card information is really compromised by the fact that a third of the money is taken out as cash from ATM machines. We don't know how it's spent. So we've got a survey at age 1, when the child's age 1, a survey at age 2, and a survey at age 3. And all those surveys were asking a lot of expenditure questions. How much money did you spend on books for your child? How much money did you spend, on computers? We've got this whole inventory of child-based expenditures, rent, food, all the kind of major expenditures that families might be making. We wanted to make this as policy relevant as possible. You know, there's a lot of, you've been following the news about Biden's stimulus plan that just passed, right? That has a $3,600 child allowance paid monthly for every child under the age of 6, and it's $3,000 per year for every child older than age 6. So this turns out to be almost exactly what was just passed in legislation. The Biden proposal, or the Biden almost law, it's going to be passed and signed into law this week, is only for 1 year. There were hopes that it would be a permanent feature of U.S. social policy. Almost all other advanced countries have child allowances, right? We don't. So this might be an entree into a child allowance every year for U.S. families. But the legislation only has money for 1 year of this. But it's, you know, we want it to be as relevant as possible. So if you look at the debate over the last couple weeks, you know, the conservatives are talking about that it's going to discourage work, this child allowance. So we're measuring work. And Maria Salvo has a almost paper showing what the impacts of this high versus low cash are on work effort over the first year of life. We, you know, part of the naysaying is, oh, these moms are just going to waste the money. They're going to spend it on alcohol. They're going to spend it on cigarettes. They're going to spend it on other things. So we actually measured those things too. And someone, who is it? Oh, Paul. Paul, who's working on the project, is analyzing impacts on these so-called temptation goods. So he's almost ready. I'm looking at your picture, Paul. Are you working on the paper right now? But you know, you can see how we didn't realize that this would be so timely, and we don't want to put any preliminary findings out until they've been peer reviewed and, you know, squeaky clean in terms of having been peer reviewed. So we want to get paper drafts submitted to journals as soon as we can, so that they're the articles might be out before the fall. The fall is probably when the debate over refunding, continuation of funding for these proposals is. So buried somewhere might be your answer, the answer to your question. Did I answer your question?
Yeah, you did. I guess I'm also curious, like, how you would maybe test to see, like, if what the mother spends the money on affects the child outcomes.
Yeah, so that's a great question. You know, it's a mediational question. And we did have a kind of a theory of change where the cash gifts, income supplementation would affect child outcomes either through a kind of a what money can buy pathway. This is the one that economists obviously talk about, versus a kind of a maternal stress pathway. So the idea of what money can buy, you know, if you're able to buy books for your child, or if the money can be used to prevent eviction and a lot of other, you know, terrible things that often happen to low-income families. If that monthly payment can kind of smooth out those potential problems, children could benefit from that. On the other hand, or maybe supplementing that, you could imagine these steady cash gifts reducing maternal stress, improving maternal mental health more generally, which may translate into more positive parenting, which in turn might lead to better child outcomes, right? So those were the two main pathways that we saw at work here. And, you know, in addition to measuring child outcomes, you really can't measure child outcomes very reliably until age 3 or 4. But our age 1 and age 2 interviews very much focus on these kind of measures. So we've got anxiety, we've got depression, you know, we've got all sorts of happiness, hope. We have all sorts of standardized scales for stress. We're also getting consent to take a little snip of hair, and we're measuring cortisol in the hair as a measure of stress hormone. And, you know, we're also at age 1, you know, COVID hit about 2/3 of the way through age 1. So we only have home interviews from 2/3 of the sample. But in those home interviews, we were able to set up a little videotaping of a parent-child play task. So we have those videos and we've coded them up for various dimensions of parent responsivity to the child. So, you know, we're in the process of analyzing that now. But, you know, you can look at treatment control differences in all these components of things that the economists say are important, all these components of what psychologists say are important. Those are impact analyses that we're running now. Eventually, we'll be able to do an impact analysis on child outcomes. You know, mediational models, as I, you know, tried to explain in the little asynchronous session, this is a really solid treatment control difference impact. Random assignment, you've got causation there. Same thing, you've got causation here. And, you know, if you take these two things away at age 3, we're going to have causation running to child outcomes. What we don't have are causal estimates of the impact of what money can buy elements on child outcomes, causal impacts of maternal stress on child outcomes, right? We didn't manipulate what money can buy. We didn't manipulate expenditures. We manipulated cash gifts. We didn't experimentally manipulate depression. It only might be occurring indirectly from the things that we did manipulate. So, you know, a mediational analysis is, we could do, you know, we could estimate these models and see what we come up with for these paths. But if we really don't trust non-experimental paths, all we can do is estimate these paths, estimate these paths, estimate the total effect over here. And, you know, if something is showing up as not being affected by treatment control differences, some expenditure, some maternal mental health measure, and we're eventually getting significant child impacts, then it's unlikely that depression is a mediator, right? It's unlikely that whatever is insignificant up here is a mediator. So, you know, that's probably more than you wanted to know, but that's the kind of mediational analysis we have in mind. And this model directed us very much toward what sort of mediator should we be measuring in the study, and we're doing that. Other questions? I apologize for getting carried away. This is we've been at this. It took us 6 years to raise the money. It's I think $18 million to do the study through age 3. You know, it's 6.5 million alone for the cash gifts. If you just add up, you know, 1,000 moms, half are getting 333, half are getting 20. It's actually not 50-50, and I'll explain that in a second. It's 60-40, but you just add those up and it's 40 months and it ends up being $6,500,000. So we had to raise all that, and then we had to raise money to do the research, which we did. But that's the background. But we need to do this power analysis, right? In order to get the money, we needed to do a power analysis to ask how big a sample did we need to be able to detect a 0.20 standard deviation difference in this case, cognitive functioning. So that's the power analysis question. And that's why things like G-Power exist.
Can I ask you a quick question? Sorry, just because what you're about
Sure.
to go over might make more sense to me. It doesn't seem like this matters, but I want to make sure it doesn't matter. Your outcomes are very wide and vast. So when we talk about a difference, we're talking about a difference in outcome, right? Or is it just between the groups? Do you have to think through how the outcome will be measured when you're thinking about power?
I'm not sure I understand. I'm not sure I understand the question.
So you're looking for a difference between the two groups based on the amount of money they're getting, right?
Right,
A difference in outcome, right?
right. And we're,
So
you know, for convenience, we're standardizing everything.
Yeah.
And so the 0.20 kind of works as it applies to standard deviations. Some of the outcomes, in fact, are not measured in standard deviations, but for purposes of illustration, this is what we're just keeping it all in standard deviation units.
So, yeah, okay. So even when things are standardized, like the difference between cortisol levels and EEG is very different to me. So I'm just having trouble understanding how we're preparing to understand the outcomes when the outcomes are very different and have very different units.
They're very different units, but that's what standardization is all about, right? You know, cortisol it has a standard deviation, and you can express treatment control differences in cortisol levels as a fraction of the control group standard deviation on cortisol, right? And then for IQ test, you know, we use a norm test, and standardization is easier there. But on everything, we can just take the raw difference between the treatment and control group, the high and low cash gift group, and divide by whatever the standard deviation of the control group is on that measure. And then we get this, this effect size measured in standard deviation units that's going to be comparable across all the measures.
It's like magic. Great, thank you.
Yeah, I mean, it's nice to have a little bit of magic. But that is the appeal of standardization. You know, we've got we did pre-registration of all our outcomes. I think there are 40 or so pre-registered hypotheses that we've got. So we've got just a ton of things. Most are these family process variables and not the child outcome variables. But you'd really like to be able to look across them all and compare impacts in some sort of comparable way. And standardization gives us exactly what we need.
Yeah, I think sometimes I jump to meaning making a little too fast. Like, does it actually matter if there's a standard deviation in cortisol versus EEG? I mean, maybe that doesn't matter at this stage. But I
No.
guess
That's
the critique is not on standardization, but it's like, okay, how do I actually make meaning out of this standardized model?
Your point is very well taken, right? We can just statistically, it's easy to standardize everything, but what does a 0.20 standard deviation really mean for a child's life chances, right? That's or what sort of a difference in family life does a 0.2 standard deviations in, spending on books or in some sort of index of parent-child activities? What does that really amount to? And those are all very good questions, and you should always be thinking of what the units mean, even if you can just do this, simple standardization to be able to compare things across the different measures that we're gathering impacts for. So good point, and keep it in mind as we talk about some of these results. Okay, so ready to move on to the actual power analysis. It's been so much fun. Do we need a break, or should I just power through this? So, I'm always in this situation where I want to power through, and I always get the impression that people are in situations where they want to take a break. So, oh yeah, about power. So email or chat Paul and let him know whether you want to keep going or not. And we'll take majority view. 30 seconds. Chat Paul. Paul will tell me. All right. What's the vote?
There are
Let's keep-
at least 11 breaks. So
All right. See you in 7 minutes at 2:20. All right. We should pause the recording, Paul. All right, so now we're taking a look at the G-Power program. We wanted to look at differences between two independent means, right? Between our treatment and control groups. Two-tailed test. We want be able to detect an effect size of 0.2 standard deviations, 5% significance level, and the default is 95% power, but we'll go for the more standard 80% power. Okay, and let me reduce my display setting a bit to 150%. All right. Where's my calculate button? There we are. Calculate. All right. So I never know what these first two statistics are. Well, critical T 1.96. But the bottom line is the bottom, well, almost bottom line here. It's 80% power, 0.8005 power. And we need a sample size of 788. Okay, so we were thinking we would have 20% attrition in the sample over the first 3 years. So if it were 800, we started out with 1,000 and it went down to 800. We would have enough power. We would have a higher sample size than 788 to be able to detect an effect size of 0.2 with a two-tailed 5% test, 80% power. In fact, if you play around with this, I think it's 1.98. Yeah, so 0.198 is the actual power that 800 observations gives you. So that's what we used, and we set our sample size of 1,000 in order to get 800. But then we thought, as we were trying to raise this money, we're $1 million short. So how can we raise $1 million or cut $1 million from our expenses? And it turns out that if you do an allocation not of 50-50 between the treatment and control group, but 60-40, you will save about $1 million if you do the math. So we wanted to know what sort of hit do we take in power if we go from 50-50 to 60-40. And it's easy to show with statistics. Anything, if you depart from 50-50, then you get a less efficient estimate. So G-Power provides an easy way to determine what the hit is. So it's 0.198 standard deviations if it's a 50-50 allocation. If it's 60-40, you're going to have a ratio of control group to treatment group of 1.5. All right, so now 800 isn't going to do it. And we can play around to see how much this increases. I think it's 204. Maybe 203. All right. So now we're back up at 800 cases with a 1.5 to 1, in other words, 60-40 split. And the hit on power, how much did we give up? How much bigger is the minimum detectable effect size? It goes from 0.196 to 0.203. Hardly any hit at all. Let me just show you. If you went instead of 60-40, if you went 40-60, then your allocation would be 2/3, and you get exactly the same result. So it doesn't make any difference if you got unbalanced groups, whether you put the big group first or the big group as a denominator. But let's do a big departure. Let's say we had 10 times as many controls as treatments, rather than 1.5 times as many. Whoa! So now you can see how big a hit it is. Now all of a sudden we're up to 2,308. And our minimum detectable effect size is probably at least 0.3, 0.35. Okay, so now we've gone up from 0.2 to 0.35 as the allocation has gone from 1.5 to 1 to 10 to 1, right? So substantial departures from 50-50 really do compromise your power, but minor departures don't. So we were able to argue that in order to be able to start the project, we needed to have enough money. If we're going to promise to pay people for 40 months, we had to have the money up front. So this is a way of making sure that we had the money up front. Any questions about that?
What if, due to practical restraints, you don't have a sample size as large as you need? Do you mention that in your paper, or should you not do that? Because in other fields, I think 100 would be felt as a large enough sample, but I don't think I've seen people mentioning that, well, the sample size isn't large enough to detect this and this. So just wondering.
Yeah, well, they don't. Yeah, you don't confess to that very often, right? But in our case, this 0.2 standard deviation effect came from a literature review showing what what sample size you would need to be able to detect an impact that was actually plausible given the literature. So we were stuck with a 0.2 standard deviation impact. And if if we only had money to recruit 800 families initially and might have 600 after 3 years, we wouldn't get the money. We would not have enough power to have an 80% chance of detecting the 0.2 standard deviation. So you're kind of stuck. And people, well, if you think about some of the classic experiments in education, the Perry preschool education, Perry preschool intervention, or the Abecedarian intervention, they had 120 kids altogether, evenly divided, right? And if you do the math, we can just do it here, two-tailed test. Let's say 0.4. Can you detect? Let's go back to a 1-to-1 allocation here. No, you can't. You don't have the power to detect 0.4. How about 0.45? Nope. How about maybe 0.48?
Greg.
Yeah.
I'm not
Oh,
sure.
I didn't share my screen. Sorry, I've been happily manipulating the G-power parameter. So I've been playing around. I started with 0.4, and this was a number that was much bigger than 120. I'm up to 0.48. Let me do 0.5. So it's easy to kind of play around with these parameters. So now we're about down to 120, right? So Perry and Abecedarian were powered to detect an enormous effect size, 0.5 standard deviations, right? So, luckily they had big impacts, but I think someone starting an early intervention project would be ill-advised to have a small sample size. And you wouldn't be able to get it past reviewers. If I was a reviewer and someone had this kind of power calculation, I'd want to have real solid evidence that this intervention could actually generate such a whopping difference between treatment and control groups. And interventions, you want to know about both short-term impacts and longer-term impacts. So I want to be able to detect a difference not just at the end of the Perry preschool. I want to know whether those effects persist 5 years later or 20 years later. And it's the same cruel math for the power calculations, right? If you want to detect a difference 20 years later, you still only have, you have 80% power to detect a half a standard deviation difference. So, I don't think a Perry preschool proposal would get very far in a review stage right now, for good reason, because it's woefully underpowered, basically. But they lucked out because a lot of their impacts are quite big. But as I say, in education interventions, it's rare when you get more than like a 0.2 standard deviation impact. If you have class size differences, instead of having 22 or 23 kids in the early grades, you've got 16, pretty dramatic reduction in class size. That had an impact in the early grades of maybe 0.15, 0.2 standard deviations. It's really hard in a scaled up education experiment to get an impact that's more than 0.2 or so standard deviations. So, you need to find a way to fund a big study, which is kind of a cruel fact of life. Okay, let me turn to optimal design, which is the second. That's my grandson, by the way, always ready for action. All right. So let's take a look at optimal design. So this is set up a little bit differently. Optimal design You can use it for doing the kind of simple calculations that we have been doing. It's really designed to take advantage of instances where you've got clustering, where you've got kids clustered within classrooms in particular, because that's often what you've got in a education experiment. You might be allocating an entire classroom to a professional development, a teacher for a third grade classroom to a professional development versus not. And there, the fact that the kids are not independent from one another, this is what I discuss in the asynchronous lecture that I posted yesterday. But anyway, so optimal design is set up for that. The problem set is going to take you into that a bit. But let's just play around with a couple more parameters. We've got a person randomized trial, a single level trial, and you get an idea of what the display is here. It's much nicer, actually. You set the significance level, we'll keep it the same, 0.05. Effect size, we want to be able to detect the 0.2 standard deviation effect size, so that's okay. And we want to know how many subjects, but the default graph only goes up to 200. So we need to rescale. That's the range of the x-axis. Let's go all the way up to 1,000. All right. So this is power, and here's our 80% power by number of subjects. You can get various kind of graphs. It's a really cool program. And instead of plugging in different values, you can just click on the line. That's 82% power, 81% power, 79% power. It's still a little annoying. Very close. 0.797 power. And here you go. Here's the 778 that we saw before. Right, if we had set this at 0.1, what was it, 0.196, 0.198, 0.198, right? It shifts around a little bit. Anyway, now we're up to 800. You can see the N here. Okay, so that gives you the same thing that you had before. What I wanted to do with optimal design is show you how much more power you get when you've got a baseline covariate that's strongly associated with your dependent variable. Okay, so with baby's first years, there is no 1-day-old measure of cognitive functioning that we can take at baseline before random assignment that correlates highly with age 3 cognitive functioning. But in educational interventions, you'll often have a covariate. If you do a let's say intervention in 3rd grade, you're trying to increase pro-social behavior. You can get a measure of pro-social behavior at baseline before random assignment, and then at the end of the treatment. And the correlation between pro-social behavior before and after the treatment is going to be pretty big, right? And the more of that correlation you have, the higher the R-square, the lower the residual variance, and the more power you've got. So let's see what actual difference it makes, right? So this is the proportion of variance in your outcome, in our case, cognitive functioning, explained by some baseline covariate. And the default was nothing. There's no explanation. But let's say we had a great baseline measure that generated an R-square of 0.25, or suppose we had a super correlated baseline variable that had a generated explained variance of 0.50. This makes a difference, right? This is our original 80% power, 800 cases, n equals 800. If we were able to include a baseline covariate that correlated, had an R square in explaining our outcome of 25%, now all of a sudden, our power needs drop from 800 to 600. We only need 600 cases to get the same 80% power. And if we've got a lot of explanation from a baseline covariate, now we're down to 300, right? So you can gain a tremendous amount of power if you've got a baseline covariate that explains your dependent variable. So in other words, pretest measures on your outcomes, which, not in the case of newborns, but in most cases that you're dealing with, the more of those you put in, the higher the R square you have in your impact equation, right? Impact is age 3. Well, let's say you've got 4th grade test scores or socio-emotional behavior, pro-social behavior as a function of, and that's in 4th grade. Let's say your intervention was in 3rd grade. At the beginning of 3rd grade, you go in and you measure pro-social behavior and a lot of other kind of behavioral outcomes. If those 3rd grade pre-intervention measures account for 50% of the variation in your 4th grade pro-social behavior outcome, you can get by with less than half of the observations and still get 80% power. All right, so that's that's one of the most important lessons I think coming out of this power analysis. Get a powerful set of baseline variables because that will help you out. Any questions about that? Okay. All right, so let's stop sharing for a moment and then talk about the second element. I said you could either run the programs or you could look at standard errors. So let's talk about standard errors for a moment. There's this direct connection between standard errors and power. What's this number? 2.8. Everyone put 2.8 in the chat. 2.8, 2.8, 2.8, 2.8. All right, keep going. Keep going. Is that everybody? Wait a minute, Lauren. Okay, thank you. Oh, 8. What? Okay. Now in the chat, spell out TWOPOINT I'm trying to cement this number in your minds. Come on. 2.8, 2.8. Okay, Lauren, I'm checking for you. Did I miss Lauren? Oh, there's Lauren. Oh. Lauren. What's the deal? Okay, so I hope 2.8 is sealed up in your mind, because 2.8 is that number. I didn't cue this up, but if you look at the Bloom article, let's go into my files here. Week 7, week 10, Bloom. Oops. All right, let me share my screen again. There's this table, table 1, minimum detectable effects as a multiple, the standard error of impact estimate for different levels of statistical power and statistical significance. So this is incredibly valuable, right? This 2.8 is the factor by which you multiply a standard error to determine 80% power at the 0.05 level in a two-tailed hypothesis test. 2.8. So if I can find a data set that has some measure of children's cognitive functioning at age 3, and which we can, we use Fragile Families, which is a data set that follows a birth cohort of 5,000 kids. They're still following those kids. But we selected 4 cities where kids were recruited, babies, in birth hospitals, same kind of design as babies' first years. So in those 4 cities, there were 800 births, our kind of target number. And we wanted to confirm that we would have adequate power to detect 0.2 standard deviation difference. So what we wanted was, there wasn't random assignment in Fragile Families, but there was child gender, almost neatly dichotomous, close enough, randomly assigned, pretty much. So we could regress age 3 test scores on child gender. Forget about what the coefficient is, but we can look at the standard error. And that gives us a guide to what sort of power we can get with a sample of 800 with a two-tailed hypothesis test at a 0.05 level, right? And if Bloom is right, and the multiplication factor is 2.8, then we should be able to take a 0.2 standard deviation effect size, divide it by 2.8, and get the standard error that's coming out of Fragile Families, right? If Fragile Families gender affecting child cognitive outcomes, if that estimate is a standard error of, let's say, 0.07, multiplying that by 2.8 gives you about a 0.2 standard deviation level of power, right? 80% power, two-tailed test and everything. So we looked to Fragile Families and did that calculation, and we got exactly 0.07. It's 0.072, I think. If you divide 0.2 by 2.8, you get 0.0714. So that confirmed that that our calculation was reasonable, and furthermore, it allowed for a couple other explorations. But let me first ask. The Bloom article is a very good one to read. The bottom line is this kind of 2.8. So, let's say that you have a data set. You don't have an experiment, but you want to see if a relatively small data set is going to have enough power to do an analysis you want to do in that data set. Let's say the data set has nice either independent variables or dependent variables. If you want to know what the power is, well, from the literature, you should ask yourself, well, what sort of effect size do you want to be able to detect? But then to see whether this relatively small data set is going to have enough power, you can use, ECLSK or some other data set you can readily access, randomly select, let's say it's 200 observations in the target data set, come up with a measure that's, roughly similar to what your dependent variable is, come up with a measure that's roughly similar to your independent variable, and see what the standard error is, right? And take that standard error, multiply by 2.8, and that gives you your minimum detectable effect size with an 80% criterion, 0.05 significance level, two-tailed hypothesis test. So let me ask for questions here.
So the 2.8 is the multiplication of 0.05 of the significance level and the standard error?
It is the multiplication factor for the standard error that gives you a minimum detectable effect size corresponding to 80% power to be able to detect, it's what I just erased. But it's, minimum detectable effect size is all about, you want an 80% chance of being able to detect the minimum detectable effect size if that is a true effect, right? You want your sample to be able to tell you that is indeed a real effect 80% of the time. That's what the 80% power is all about. So if you think about the example, we looked at G power, it gave us 800 as a sample size needed to detect with 80% probability a 0.20 standard deviation impact, right? 5% significance level, two-tailed test. So that means, if we went out and gathered 800 observations, it ought to be powered enough to be able to detect a 0.2 standard deviation impact. What Bloom shows in his article is that if I take an 800 case data set and come up with a dependent variable that's similar to our dependent variable, come up with an independent variable that is similar to our experimental control contrast, and child gender is a good example of that. Again, I don't care what the coefficient is for child gender differences. I just want to know what the standard error is. And that standard error on 800 cases, if multiplied by 2.8, should give me the same result that the G-power calculation does. And in fact, it does. It produces a standard error on the gender variable that's 0.07 something. So when you multiply that by 2.8, it's saying, yes, those 800 cases are sufficient to generate a minimum detectable effect size of 0.20 standard deviations 80% of the time.
There are just too many different terms and units that are bouncing around in my head.
Yeah, no, I'm sympathetic. So, sometimes you're able to do a G-power approach. You've got an experiment, you've got from the literature an idea of what sort of effect you want to be able to detect. In our case, it was 0.20 standard deviations, right? So we want to know if the effect really is 0.2 standard deviations, are we going to be able to detect it most of the time, right? 80% of the time. Crank it through, you need 800 cases after 3 years to be able to detect that. So if that's what you're doing, planning for an experiment, just use G-power. Or if it's a clustered design, you got kids clustered within classrooms, use optimal design because that accounts for clustering. But on the other hand, suppose you just want to do some kind of regression analysis, not an experiment, but some kind of regression analysis, right? And there's a data set that you might make a big investment in getting to know. It only has 200 cases, but it really has the variables that you need, right? Is it going to be able, is it going to be the situation I put up on the board, a 0.25 standard deviation impact with a standard error of 0.20, right? That's kind of where we started this conversation. And if that's the case, then you're sunk, right? You're not, it looks like a respectable effect size, but you can't tell that it's different from 0. And what doomed you was the fact that your sample size was too small. So, if you see a nice data set, it's going to give you the variables you want. The question is it going to give you the effect size that you want? Will you be able to detect an effect size that you want? And for that, you really can't crank it through with G-Power very easily. Finding some parallel data set that, let's say you're interested in executive function, and the new NLS or ECLSK has a decent measure of executive function. It doesn't have to be as high quality as the one you're going to end up with. It just has to be pretty close. And then there's some independent variable of interest that you can also approximate in the data set that's readily at hand. Run that regression in the data set you've got at hand. Look at the standard error on your independent variable of interest, multiply by 2.8, and that will tell you whether this 200 case data set is going to, you have to subset that data set that you know down to 200 cases, run the regression, see what the standard error is. And then, maybe it's the minimum detectable effect size is going to be 0.4. You were hoping for 0.25. Add in another 200 cases, so you've got 400 instead of 200. See what standard error does. And, you can kind of iterate down to exactly what you want that way. But, the big virtue of all this is that it can avoid a lot of the heartbreak of a 0.25 standard deviation coefficient and a 0.20 standard error. You don't want to be in that situation, right? You've wasted all your time with that data set. It just wasn't powered. It just didn't have enough observations to provide enough power that you really needed. And you want to know that right up front, rather than after all the investment that you make in that new data set. Is that a little bit clearer?
I have it. So I guess the distinction then is that you use G-Power and optimal design to plan for a study versus the standard errors once you have the data. So if you're using like existing data as we are to see would we have enough power based on the standard error of the variable that we're interested on.
Exactly. I couldn't have stated it better myself.
Thank you.
Okay. So let me just close with sharing my screen again and show you what our proposal actually had as a power section. So when you do a proposal for IES or NICHD, you've got to demonstrate adequate power, right? So here's what our power section said. Compensation difference between families in the experimental and control groups amounts to $313 a month, right? 333 minus 20, and $12,520 over the course of the 40 months. This amount is in the range of income increases associated with child impacts of about 2.2 standard deviations, right? That's what we get from literature in studies of welfare experiments and the earned income tax credit. After accounting for likely 20% attrition, and in the absence of adjustments for sample clustering within hospitals or increased precision owing to the inclusion of baseline covariates, right? A couple of things we talked about. The sample size of 800 at age 3, evenly divided between treatment and control groups, provides 80% statistical power to detect a 0.198 standard deviation impact at p less than 0.05 in a two-tailed test. Right, 0.198. That sounds familiar. That I got this number out of GPower. Okay, given the directional nature of our hypotheses, it can be argued that a one-tailed test is more appropriate, in which case our 80% power minimum detectable effect size drops to 0.177. So, we stuck with a two-tailed test to be more conservative, but this gives you an idea. If you go from two-tailed to one-tailed, you get this 0.02 or so deduction in minimum detectable effect size. All right, baseline covariates improve this power. That's what we saw from optimal design. While sample clustering within hospitals, the fact that the observations may not be completely independent from one another, will reduce it. To gauge the likely magnitude of these offsetting effects, we obtained data from the Fragile Families Birth Cohort study, modeling age 3 child receptive vocabulary scores. It's kind of a cognitive test. This is the Peabody Picture Vocabulary Test, as a function of an essentially randomly designed variable with a roughly similar, well, actually we don't need the roughly similar hypothesized effect size, child gender. We're not interested in the coefficient, we're interested in standard error. So from Fragile Families, we selected all births in 4 large cities to obtain a sample size of 821. A simple bivariate regression of the cognitive measure on child gender with no adjustment for sample clustering generates a standard error of 0.073. Using Bloom's rule of thumb multiplier of 2.8 to convert standard errors into 80% power with two-tailed alpha of 0.05, we obtain a corresponding minimum detectable effect size of 0.204, right? Nicely corresponding to the 198. But what's nice here is not just to show Bloom was right, but now we can play around with clustering, right? We can adjust for city-based clustering, which actually this is a typo. There was a very small increase in the minimum detectable effect size. I think it was like 0.208. The intra-class correlation, this is the extent of clustering of cases within hospitals. The inclusion of baseline demographic covariates. So we'd really like to have a baseline cognitive measure, but we don't. But we do have maternal education, co-resident father, and so forth. Reduces the minimum detectable effect size to 0.188. A rather small amount reflecting the lack of baseline covariates that are strongly predictive of individual variation in child language. In some clustering by city and including covariates will have minimal and offsetting effects on statistical power. Okay, so this page is in on the syllabus. There's a link to it, but you can see, right, how all these things you can pull together, where you get agreement between GPower and this kind of regression approach. And the nice thing about a regression approach, you can't with GPower understand how much baseline covariates might actually help you out, what the R-square would be with baseline covariates predicting child IQ. So actually looking at a data set gives you an idea of how much you might be able to gain in terms of power. And in fact, you gain a little bit from 0.20 to 0.188, not very much. So, in the experiment, we've got these baseline covariates, so we're going to have a little bit more power from them, but it's not a big deal. Nor is the clustering of kids within hospitals a very big deal. So what you get out of GPower in this case is a very good guide to what our impact minimum detectable effect size should be. And we are sworn to secrecy on what the first year impacts are. You can probably bribe Paul into giving you, but we do know when we standardize age 1 impacts, we get standardized standard errors of about 0.07. You know, it's exactly what we expected them to be. So it all kind of meshes together in this power calculation. But you know, you need to do this to get money, research money. But as a practical matter, you also need to do this if you're interested in any sort of quantitative analysis to make sure you've got enough observations to be able to detect the kind of impacts you want to be able to detect. All right. Any questions about that? With the assignment, you'll play around with G-Power, play around with optimal design, and play a little bit around, you know, this trade-off between 50-50 versus 60-40, saving you money. That turns out to be pretty important. You know, oftentimes you'll have if you're doing intervention, the intervention won't be cheap. It'll be, you know, a couple $1,000s per child, maybe. And maybe a 50-50 allocation isn't the best. If you make it 60-40 or 70-30, you don't lose that much power, and you have a lot more money to increase the total sample size, right? So there are those kind of considerations too when you actually go about designing an analysis.